Today, we're going to continue the discussions for the applications of volume. So I will call this one as part two, application on finding the volume of the solid of revolution. I have here, so solids with known cross sections. So with this method, you can find the volume of a solid having a circular cross section whose area is A is equal to pi r squared. So this method can be generalized to solids of any shape as long as you know a formula for the area of an arbitrary cross section. So some common cross sections are squares, rectangles, triangles, semicircles, and trapezoids. So just recall the formula for those areas of those cross sections. So volumes of solids with known cross sections. So number one, for cross section of area A of x taken perpendicular to the x-axis. So the formula is volume is equal to the integral of A of x dx. So with the limits of A to B. Number two, for cross sections of area A sub y taken perpendicular to the y-axis. So volume is equal to the integral of ay dy, so with the intervals from C to D, as you can see in the figure. So let's go first for the definition. So the volume of a solid of integrable cross-sectional area, shall we say A of x, from x equals A to x equals b. So it refers to the intervals or the limits. It is the integral of a from a to b. So volume now is equal to the area of a of x dx from a to b. So these definitions applies whenever a of x is integrable, and in particular, when it is continuous. So to apply the definition to calculate the volume of a solid, take the following steps. So these are the steps in calculating the volume of a solid. So number one, so sketch the solid and a typical cross section. Number two, find a formula for A of x, which is actually the area of a typical cross section. And the third step, we have find the limits of integration. And the last step now is we have integrate A of x to find the volume. Okay, for example, a pyramid 3 meters high has a square base that is 3 meters on a side. So the cross section of the pyramid perpendicular to the altitude x meters down from the vertex is a square x meters on a side. So find the volume of the pyramid. So take a look on the figure 6.5 on the right side. So this is the cross section of pyramid in example number 1. So the cross section there is a square. So first, according to the steps, so number 1, we have to sketch. So we draw the pyramid with the altitude along the x-axis and its vertex at the origin. So I'm referring to this, and include a typical cross section. So let's just look at here in the figure 6.5. So step 2, so finding the formula for the A of x. So the cross section of x is a square. This one, x meters on the side. So its area is A of x equal to x squared. Number 3, so the limits of integration. So we have the squares lie on the planes from x equals 0 to 3. So and then step 4, we have to integrate to find the volume. So let us solve. So we have here for the volume now is equal to the integral of A of x dx from A to B. So from our problem, it says that the cross section is a square. So therefore, the formula there will be x squared. So we can write here x squared dx. X squared here is the meaning of A of x. And then from the interval of A to B, so which is now from 0 to 3. Then we have to integrate this one. So the integration of this is x cubed over 3, and this will be evaluated from 0 to 3. So taking the evaluation for this by using the fundamental theorem of calculus, it will just give us the answer of 9 cubic meters. So that's the volume for that problem. Number two, a curved wedge is cut from a cylinder of radius 3 by two planes. One plane is perpendicular to the axis of the cylinder, and the second plane crosses the first plane at a 45 degrees angle at the center of the cylinder. So find the volume of the wedge. So first, we're going to draw the wedge and sketch a typical cross-section perpendicular to the x-axis. Kindly just refer to the figure below. So we have here now the figure for this problem. So the base of the wedge in the figure is a semicircle. So that is now the semicircle. So the base of the wedge in the figure is the semicircle with x is greater than or equal to 0, that is cut from the circle x squared plus y squared equals 9. 9 because the radius is 3, so therefore x squared plus y squared equals r squared is equal to, the r squared there becomes 9. So the base of the wedge in the figure is the semicircle with x is greater than or equal to 0, that is cut from the circle x squared plus y squared equals 9 by the 45 degrees plane when it intersects the y-axis. Okay, so for any x in the interval of 0, 3, so the y values in this semicircular base can be solved from the circle. So we have x squared plus y squared equals r squared. So this is now x squared plus y squared equals, your r is 3, so therefore 3 squared is 9. And after that, we're going to solve for y. So we have y squared is equal to 9 minus x squared. So taking the square of both sides, so therefore y is equal to plus and minus the square root of 9 minus x squared. So that is why the y values in the semicircular base vary from y equals negative square root of 9 minus x squared to y equals the positive value of this. We have square root of 9 minus x squared. So when we slice through the wedge of a plane perpendicular to the x-axis, we obtain a cross-section at x, which is a rectangle of height x, whose width extends across the semicircular base. So the area of this cross-section, so we have now the area of this cross-section, shall we say A of x, will be equal to the height times the width. So we know that the height there is x, this one. So we have x, and the width now is, the width is this one. We have 2 square root of 9 minus x squared. So multiplying that one, that can be now the area of the A of x, or the area of a cross section. So we have now 2x times the square root of 9 minus x squared. So now we have now the formula for A of x. Looking at to the figure, so we have the limits from 0 to 3. So we have here the rectangle run from, so the rectangle run from x equals 0 to x equals 3. So I'm referring to this one. Okay, so we can now have the formula for our volume. So we have V is equal to the integral of A of x dx from 0 to 3. So by substituting the value of your area, or A of x, we have now 2x square root of 9 minus x squared from 0 to 3. So integrating that one, we are going to let, I will just write here, let u is equal to 9 minus x squared, and du now equals negative 2x dx. If I'm going to compare this one to our given, so I supposed to have dx here. So I have 2x dx, which can be represented by du. Since I have negative sign there, so I divide both sides by negative or multiply by negative. Therefore, I have negative du is equal to 2x dx. So, continuation in this part. So, we have v is equal to the negative of the integral of this one is our u. We have u raised to 1 half, and 2x dx is our du. We have a coefficient factor of negative 1, so I write outside. And now integrating that one, so we can write now as the negative 2/3 of u to the power of 3 halves, and that will be evaluated from 0 to 3. So by substituting the value of u, so we can write now negative 2/3 of our u is 9 minus x squared, and then to the power of 3 halves, and with the interval from 0 to 3. So taking the fundamental theorem of calculus to evaluate the integrals, so this will give us now the answer of 18. Okay, number 3. The solid lies between planes perpendicular to the x-axis at x equals -1 and x equals +1. The cross sections perpendicular to the x-axis are circular discs whose diameters run from the parabola y equals x squared to the parabola y equals 2 minus x squared. So as it is represented to our graph or figure. So first, I'll try to follow now the steps. So we are going to identify first our formula for a of x. So we have now a of x. Since the cross section is perpendicular to the x-axis at circular disc, so we can have now the formula for that from the circular disc. We have here pi of diameter squared over 4. So that's the area for the circular disc. So we are going to substitute now. So we have pi is equal to, the diameter is actually the difference between the two functions. This one, the upper function, we have 2 minus x squared. 2 minus x squared. And then minus the other one is x squared. So minus x squared, and then square all over 4. By simplifying that, we can now have here, subtract this one. So we have pi times, we have 2 minus 2x squared. And then this will be, the quantity is raised to the power of 2. So by simplifying that one again, so I have a common factor of 2. So I have pi times 2 times 1 minus x squared. This bracket will be squared over 4. So simplifying further, so taking now the power of 2 from the bracket, so we have 2 squared, it becomes 4, and 4 divided by 4 is 1. So I can cancel that one. So what is the remaining here is just pi times the square of 1 minus x squared. We have 1 minus 2x squared plus x to the power of 4. So we don't have any more 4, denominator 4, because we canceled a while ago. So therefore, this is our a of x. Now, after knowing the a of x, or the area of the cross sections, now we can solve for the volume. So we have volume is equal to, our formula is, we have the integral of a of x dx from a to b. So to know the value of the limits, it's part of the given. So therefore, we know that a equals -1 and b is equal to 1. So by substitution, so we have now a of x, which is now pi times 1 minus 2x squared plus x raised to 4 of dx, and from negative 1 to 1. So simplifying that one, so I will just write the pi outside the integral sign. So we have pi and then integrating this one. So we can write now the integral of 1 is x minus 2x cubed over 3 plus x raised to 5 over 5 from the interval of negative 1 to positive 1. Okay, so by evaluating that one, so the final answer now will give us 16 pi over 15. And that is now our volume. So number 4, the base of a solid is the region between the curve y equals 2 square root of sine x and the interval from 0 to pi on the x-axis. So the cross sections perpendicular to the x-axis are letter A, equilateral triangles with bases running from the x-axis to the curve shown in the figure. In letter B, the cross-section perpendicular to the x-axis is squares with bases running from the x-axis to the curve. Now let us try to solve first for letter A. So step 1, we're going to find the formula for the A of x. So we have A of x. Take note that the base here is the cross section is the equilateral triangle. So we have now the formula for the area of that. We have 1/2 of side times the other side, and the height there is sine of pi over 3. So the side now is equivalent to 2 square root of sine x. So by substitution, I have 1/2 times 2 square root of sine x. Then the other one is the same because that is equilateral. So we have 2 square root of sine x times sine of pi over 3. So by simplifying that one, so we can write now, so 2 times 2, we have 4 divided by 2 from the 1/2. Therefore, it gives us now 2, and the square root of sine x and square root of sine x is just now sine x. So we have now 2 sine x times we have sine of pi over 3. So writing the value of sine pi over 3. So we have 2 sine x times the value of sine pi over 3 is the square root of 3 over 2. Now, therefore, a of x now, so simplifying it, 2 sine x times square root of 3 over 2. So 2 is cancelled. So we have now sine x times square root of 3, whose product now is square root of 3 of sine x. So that is now a of x. Now we are going to write the formula for the volume. We have a of x dx from a to b. So our interval for this problem is given which have 0 pi. So a is 0, b is pi. So I will write there from a to b. So by substitution, so we have now square root of 3 of sine x dx. So value of a is 0 and value of b is pi. So after that, we are going to integrate. So integrating that one, it will give us now, we have the square root of 3 and the integral of sine x is negative. So we can write down the negative square root of 3 of cosine x. This will be evaluated from 0 to pi. So using the fundamental theorem of calculus, so this will give us now the answer of the volume now becomes 2 square root of 3. That's the answer for letter A. While for letter B, so since the cross section is perpendicular to the x-axis, we have squares with bases running from the x-axis to the curve. So our A of x now will be just equal to side or the square of the side because we are referring to the squares. So by substitution, we know that the side is the 2 square root of sine x. So I will write here 2 square root of sine x and this will be squared. So I supposed to write here e of x, and then we have here a of x now will give you now the answer is squaring this one. This will give you as 4 sine x. Now we're going to write for the formula of the volume. So volume now is equal to the a of x dx from A to B. So by substitution, A of x now we have 4 sine x. So we have 4 sine x dx. So the interval is the same from 0 to pi with the same with respect to the question letter A. So we have now 0 to pi. So by integrating that one, so we have now, I will write first 4 outside and the integral of sine x dx. So the integral of sine is negative cosine. So we can have now negative 4 cosine x, and this will be evaluated from 0 to pi. So by using again the knowledge of fundamental theorem of calculus, so this will give us the answer of 8. That's the volume. Okay, number 5, find the volume of the solid shown below. So I'm preparing here the figure. So the base of the solid is the region bounded by the lines f of x equals 1 minus x over 2, and g of x equals negative 1 plus x over 2, and x equals 0. So the cross sections perpendicular to the x-axis are equilateral triangles. So to solve for this, we're going to find the base and area of each triangular cross section. So we start now from the base. So to solve for the base, according to this problem, it's actually the difference between the two functions. So because the base there, it refers to the length of the base. So looking at the length of the base, so we can have this one, the length of that, of the two functions. So we can have now the difference between the f of x minus g of x. So we have here 1 minus x over 2 minus the g of x, which is now the negative 1 plus x over 2. So simplifying that one, it will just give us the answer of 2 minus x. So this is now our base. Now to solve for the area of this cross section, so we have the area is equal to the square root of 3 over 4. Since it is equilateral triangles, so we have square root of 3 over 4 times the square of the base. So since we solved earlier the base, so we will just substitute it there. So we have now square root of 3 over 4 times 2 minus x. The quantity of this will be raised to the power of 2. So this is now our a of x, which is now actually the area of cross section. So from there, we are going to solve for our intervals. So solving for the intervals, we're going to equate the two functions. So we can write here as f of x is equal to g of x. So we have 1 minus x over 2, the value of f of x, while the g of x, the negative 1 plus x over 2. So combining like terms, so therefore 1, this will be transposed, becomes positive 1, so this becomes 2 is equal to x over 2 plus transpose at 1 becomes x over 2. So by simplifying that one, so we can write now here, we have 2 is equal to, they are just similar fractions, so therefore we have a common denominator of 2, so therefore 1x plus 1x, we have 2x. So solve for that, cross multiplication, so we have now 4 is equal to 2x, and divide both sides by 2, therefore we have 2 is equal to x. So we have now x equals 2, and the other one is given from x, the value is x equal to 0. So therefore the value of a is 0 and the value of b is 2. Or in other words, the lower limit is 0 and the upper limit is 2. Now from here, we can now solve for the volume. So the volume now will give us the formula of, we have a of x dx from a to b. So we have a of x, which the cross section is this one. So we have square root of 3 over 4 times the square of the base, which is now 2 minus x squared. And the intervals a to b is from 0 to 2. So simplifying that one, so I will just write a constant multiplier. So we have here square root of 3 over 4 times the integral of expanding the square binomial. We have 4 minus 4x plus x squared of dx. Then from 0 to 2. So by integrating that one, so we have square root of 3 over 4 times 4x minus 4x squared over 2, or the simplified form is 2x squared plus x cubed over 3, and this will be evaluated from 0 to 2. So by using the FTC, so this will give us now the answer of 2 square root of 3 over 3. So the last method for finding the volume is what we call now as the shell method. So in this section, you will study an alternative method for finding the volume of a solid of revolution. So this method is called now the shell method because it uses cylindrical shells. A comparison of the advantages of these and shell methods is given later in this section. So to begin, consider a representative rectangle as shown in figure 7.27, where W is the width of the rectangle, H is the height of the rectangle, and P is the distance between the axis of revolution and the center of rectangle. So when this rectangle is revolved about its axis of revolution, it forms a cylindrical shell or tube of thickness W. To find the volume of the shell, consider two cylinders. The radius of the larger cylinder corresponds to the outer radius of the shell, and the radius of the smaller cylinder corresponds to the inner radius of the shell. Because P is the average radius of the shell, you know the outer radius is P plus W over 2, and the inner radius is P minus W over 2. So this is now the outer radius. We have P plus W over 2, and the inner radius is P minus W over 2. So the volume of the shell is given by the formula. The volume of shell is equal to volume of the cylinder minus the volume of hole. So since the volume of a cylinder, whose formula now from this figure will give us pi times the square of P plus W over 2 times the height minus the volume of the hole. It refers now to the inner radius. So we have pi times the square of P minus W over 2 times the height. So by simplifying that one, volume of the shell now is equal to 2 pi PHW, or 2 pi times the average radius. The average radius is refers to the variable P, and H is for the height, and W now is for the thickness. So the shell method, to find the volume of the solid of revolution, so with the shell method, use one of the following as shown in this figure. So we need this horizontal axis of revolution. So when we use this formula, so volume is equal to V is equal to 2 pi the integral of P of y times H of y dy. So with the intervals from C to D. So this is now the horizontal, it's a figure. And the other one is the vertical axis of revolution. Is V is equal to 2 pi times the integral of P of x, H of x, dx. So with the interval from A to B. So just take a look on this figure. So for the comparison of this and the shell method, so that this and the shell method can be distinguished as follows. For this method, the representative rectangle is always perpendicular to the axis of revolution. Whereas for the shell, the representative rectangle is always parallel to the axis of revolution. So this one is for this method, that is this method representative rectangle is perpendicular to the axis of revolution, while the other one is for the shell method, whose representative rectangle is parallel to the axis of revolution. Now let's take a look on the example. So find the volume of the solid of revolution by revolving the region bounded by y equals x minus x cubed, and the x-axis, we have x is greater than or equal to 0 and x is less than or equal to 1 about the y-axis. So this is represented by the figure 7.30. To solve for this, so because the axis of revolution is vertical because of the word y-axis, so we use a vertical representative rectangle, this one. So as shown in figure 7.30, so the width, it refers to the delta x, indicates that x is the variable of integration. So the distance from the center of the rectangle to the axis of revolution is p of x equals x. And the height of the rectangle is referred to the h of x is equal to x minus x cubed. So because x ranges from 0 to 1, so we have now the volume of the solid can be written as V is equal to 2 pi times the integral of P of x, h of x, dx. Okay, from A to B. So I am referring to this formula, this one. So we have 2 pi times the integral of p of x, h of x dx from a to b. The value now of p of x, so we have 2 pi times the integral of p of x, which is now equals to x, this one. So we have x, and h of x, we have the times x minus x cubed of dx. So from the interval from 0 to 1. So simplifying that one, so we can write now as 2 pi times the integral of, we have x squared minus x to the power of 4 of dx. And then from 0 to 1. And then we are going to integrate that one. So by integrating this one, we have now 2 pi times, we have x cubed over 3 minus x to the power 5 over 5 with the interval of 0 from 0 to 1. So by evaluating our integrals, so will give us now the answer of 4 pi over 15. So number 2, find the volume of the solid of revolution formed by revolving the region bounded by the graph of x equals e raised to the negative y squared, and the y-axis, y is greater than or equal to 0 and y is less than or equal to 1 about the x-axis. So this is represented by this figure. So because axis of revolution is horizontal, so we are going to use now the horizontal representative rectangle. So as shown in this figure. So the width of delta y indicates that y is the variable of integration. So therefore, the distance from the center of the rectangle to the axis of revolution is p of y is equal to y. And the height of the rectangle is h of y is equal to e raised to the power of negative y squared. Because y ranges from 0 to 1 according to this interval, so the volume of the solid can be written as V is equal to 2 pi times the integral of P of y times h of y dy from C to D. where C is 0 and D is equals 1. So by substituting the values now, we have 2 pi times the integral of P of y, which is now y, and h of y, according to this figure, we have now e raised to times e raised to the negative y squared of dy, and c is equal to 0 and d is equal to 1. Okay, so to solve these integrals, I will let now u equals the negative y squared, and taking the derivative of that, we have du is equal to the negative 2y dy. So looking back again, the integrals, I have y dy. Since it is visible, the y dy, so therefore I will solve y dy on this. So therefore I have du over negative 2 is equal to y dy. So from there, I'm going to substitute again to the integrals in terms of u and du. So therefore, we have 2 pi times the integral of this one, e raised to the power of negative y squared can be written now as e raised to u, and y dy can be written now as du over negative 2. So multiplying this one, 2 pi with the negative 2, so we have now the negative pi, the integral of e raised to u du, and the integral of that will just give you as negative pi. So or the integral of e raised to u du is just equal to e raised to u, and then this can be evaluated from 0 to 1, which I forgot, so I will write everything here 0 to 1. I will replace the meaning of u, which is now the negative pi of e raised to the negative of y squared, evaluated from 0 to 1. So if you're going to evaluate that one now, we'll give you the answer of pi times 1 minus 1 over e, or with the approximate value of 1.986. Number 3, find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. So I'm going to solve this one using the shell method. So looking at the figure, so we can write now the formula for the volume. Volume is equal to 2 pi times the integral of p of x times h of x dx from a to b. So we have 2 pi is equal to, the value now p of x is equal to x, and the value of h of x, we have x squared plus 1, so times x squared plus 1 of dx, and the intervals now is coming from 0 to 1. So 0 to 1. So simplifying this one, we have now 2 pi times the integral of x cubed plus x of dx from 0 to 1. So integrating that one, we have 2 pi times x to the power of 4 over 4 plus x squared over 2. So it will be evaluated from 0 to 1. So by using the fundamental theorem of calculus, this will give us the value of 2 pi times, so simplifying that one will give you 3/4. So simplifying it further with 2 pi times 3/4 will give us the value of 3 pi over 2. Even if you're going to use other methods such as washer method, so the answer would be just the same. Okay, number 4, find the volume of the solid formed by revolving the region bounded by the graphs of y equals x cubed plus x plus 1, y equals 1, and x equals 1 about the line x equals 2, as shown in this figure. So in the equation y equals x cubed plus x plus 1, you cannot easily solve for x in terms of y. Okay? So therefore, the variable of integration must be x, and you should choose a vertical representative rectangle. because the rectangle is parallel to the axis of revolution. So using the shell method, so we can obtain now the formula of, so V equals 2 pi times the integral of p of x times h of x dx from a to b. So we have 2 pi equals the integral of p of x there, which means that is 2 minus x. So we have 2 minus x, and h of x, which is equivalent to x cubed plus x plus 1 minus 1. Okay, and this is of dx. So simplifying this one, this will just give us the answer of negative x raised to 4 plus 2x cubed minus x squared plus 2x of dx from 0 to 1. So this is also from 0 to 1. And then, so integrating this one will give us now 2 pi times the integration of this is negative x raised to 5 over 5 plus integration of 2x cubed is x cubed, we have x raised to 4 over 4, but that's 2 4, therefore we have x raised to 4 over 2 minus x cubed over 3 plus 2x squared over 2 is just equal to x squared. And this will be evaluated from 0 to 1. So by using the fundamental theory of calculus, so this will give us now 2 pi times, I will write the, if I'm going to evaluate 1, so this can give us the value of 1 over 5 plus 1 half minus 1 third plus 1. So minus f of a is 0, so no need to write 0. Therefore, so simplifying that one now will give us the answer of 29 pi over 15. So that's the volume.